Welcome back to Physics 151 Online. Today we're going to move into a discussion of the angular quantity that is analogous to force in linear motion, and that is torque. And in so doing, we'll be able to derive a rotational version of Newton's second law. Then we'll go on to talk a little bit about rotational energy when we have rotational motion plus translational motion, and that we call rolling motion. So first, let's consider an object of some arbitrary shape that's being rotated about an axis that goes through the origin, and we've seen this picture before, and we're going to consider the motion again of just one tiny mass element of that object. But now what we're going to do is to imagine that there's an external force that's applied to the rotating object at that point. And so what happens at that point is that there is a tendency for the object to rotate. If we want to think of a physical example, imagine that right at that point on the object there's a peg, and around that peg we wrap a string, and then we pull on the string, and so that's going to cause the object to rotate. And even though it's a force that's being applied, we think of a torque that force applies to the object about the axis of rotation. And we can express that torque in several equivalent ways. So here's the case of a force being applied vertically, straight up at that point, and it's applied so that it makes an angle theta with the radial direction, starting at the axis and moving outward, going through that point where the force is applied. And with that geometry, we can express the torque using this definition. The magnitude of the torque, and we use the Greek letter tau, is the magnitude of the force, F, multiplied by the perpendicular distance from the line of force to the axis. And in order to indicate that, we would draw a dotted line along the line of force, extending both upwards and downwards along that line, and the perpendicular distance from that dotted line to the rotation axis would be this quantity here on the right hand side. Sometimes physics books will refer to this as the lever arm or the moment arm for the torque. So extending that dotted line, like I said, downward from where the force is applied, we can see that where it crosses the x-axis, that defines the perpendicular distance from that line to the axis, and we usually refer to that as r perpendicular. Notice it's not the same as the radius or the radial distance where the force is applied. It's just a component of that. So using this definition, the torque can be written as the magnitude of the force times this r perpendicular, and using the geometry indicated in the sketch, the angle theta that the force makes with the radial direction is the same angle as the upper angle inside this right triangle. And by looking at that carefully, you see that r perpendicular can be written as r times the sine of that angle theta. So r sine theta is the same as r perpendicular. And if we want to, we can also regroup these terms to define the component of the force along the tangential direction, realizing that the object is going to undergo circular motion, and so the component of the force tangent to that direction is also going to be F times the sine of theta. So if we just group the sine of theta term with the F, we can define this tangential component of the force, because F tangential is F sine theta. And that's going to be helpful as we now want to calculate the total torque that is exerted on the entire object. Notice that for this definition to work out, the angle theta is defined in that very specific way, so that it makes the angle between the force vector and the radial vector r when the two vectors are drawn tail to tail. So you see the vector r in the sketch. If we shift it so it moves outward along the radial direction so that the f vector and the r vector are tail to tail, then that's the angle theta. So it's got a very specific meaning here. Now, let's figure out if there's going to be a tangential force that's applied to this rotating object, we'll figure out how this translates into an angular acceleration of the entire object. Okay, and we're going to use Newton's second law applied to this little mass element and then do a summation or an integral over all of the mass elements of the entire object. Okay, so just a moment ago we said that we could write down the torque as the tangential component of the force times the radial distance, and here for this little mass element, the force using Newton's second law is equal to the mass times its acceleration in the tangential direction, and then r is equal to this r sub I, the distance of that mass element away from the axis. Okay, so now we also remember that there's a relationship between the tangential acceleration and the angular acceleration of the entire object. Just as v is equal to r times omega, a is equal to r times alpha. Remember that alpha is in radians per second squared for the object. So we can substitute that into the torque equation, and that gives us now the torque is equal to delta m sub I, r sub I squared times alpha. The reason for doing this is because in the next step we want to add up all of the torques that all of the mass elements for that object experience due to that force. And when we do that, we sum up all of these terms, adding up the contributions from I equals 1 to however many mass elements we have, and the angular acceleration, since it's the same for every piece of mass in that object, the angular acceleration comes outside the summation. Okay, now this is truly only an approximation because it becomes exact in the limit where we take that mass element to be very, very small and the sum becomes an integral. And we'll complete that step in just a moment. But what we see is the alpha comes outside, and this summation you should recognize because we encountered it before where we were talking about rotational kinetic energy. It's nothing more than the moment of inertia. So there's our expression for the net torque acting on the object. This summation in the limit where delta m becomes very, very small then turns into an integral of r squared dm, and that's nothing more than the moment of inertia. So look at this equation. This is actually Newton's second law for rotational motion about a fixed axis, because it tells us on the left hand side the net torque is equal not to mass times acceleration but to the corresponding quantities for angular motion, for the moment of inertia times the angular acceleration. Compare this compare this to Newton's second law for the translational motion, and you'll see that if you can remember the sum of the forces is mass times acceleration, you can easily remember that the sum of the torques is equal to I times alpha. And these two equations together we will apply to do an example problem in class. Let me just show you the example here. You'll remember earlier in the semester we analyzed a system like this where you have two masses connected to a string, and that string is wrapped around a pulley. We considered the case where the mass of the pulley and the size of the pulley were negligible. Okay, and so that allowed us to assume that the tension on both sides of the pulley was the same in that string. Now we're going to analyze the situation more carefully, and we're going to take into account the mass of the pulley. And in order for that pulley to rotate when one of the masses falls and the other mass goes up, it's necessary, if it has mass, that these two tensions not be the same. So we'll make sure that we take that into account. So we'll work this out in class, but the basic strategy will be to analyze each of the individual masses using Newton's second law in the normal way. And then we'll get one more equation because we will write down Newton's second law for the pulley itself and add up the sum of the torques and set that equal to the moment of inertia times alpha. And by combining those equations, we'll be able to figure out the acceleration of the system. All right, and you have to be careful with signs and use the constraint equations, and I'll show how to do that in class. But using Newton's second law for rotational motion allows us now to do a more complicated problem than we could do before, where we had to assume that the mass of the pulley was negligible. Now you'll also see that in some cases, particularly where the force is given in component notation, using perhaps a unit vector notation, that it's convenient to express the definition for torque in terms of vector form. And we're going to introduce, using this definition of the torque, we're going to introduce a new notation that involves the cross product of two vectors. We've talked about how two vectors can form a dot product. That was back when we were calculating the work done by a force acting on an object. But now when there's a force acting on an object that tends to cause it to rotate, we can define the torque in terms of the force vector and also the vector that points from the axis to the point on the object where the force is applied. So this gives a vector nature for the torque. The magnitude is exactly the same. Okay, the definition of the cross product of two vectors has two parts. It first tells us that the magnitude of vector A crossed into vector B is equal to the product of the magnitudes of the two vectors times the sine of the angle between them. Of course, again, the angle is defined so that when the two vectors are drawn tail to tail, theta is the angle between them. And that's why it's the angle theta that's indicated in the sketch. If I slide the r vector out so that f and r are tail to tail, then that's the angle theta that we want to use in this cross product notation. Okay, but a cross product of two vectors, and this is how it differs from a dot product, a cross product of two vectors is itself also a vector. And so this definition gives us the magnitude, but the direction of the torque vector is given by the right-hand rule. And the right-hand rule, we can talk about this more in class, but the right-hand rule, in doing so, we extend the fingers of the right hand along the direction of the first vector, in this case A, and then curl your fingers toward the second vector, in this case B. And if you do that with your right hand, you'll find that your thumb is pointing out of the screen or out of the board. And so your thumb is pointing in the direction of the cross product of the two vectors. Now, why is this important? Well, the curling of your hand from A towards B is consistent with the rotation that would be caused by that force acting on the object. It would cause the object to rotate counterclockwise, and that would be the direction of your fingers as they rotate from the direction of A to the direction of B, right? And so rather than say that the vector torque is counterclockwise, we say that the vector torque is out of the page, and that's consistent with a curling of the fingers of the right hand in the counterclockwise direction. So this is particularly helpful if we are given R and F in component notation, because it's relatively easy to work out the cross products of the I components and the j components that make up those two vectors. Now, let's move on to finish this introduction by considering rolling motion. And rolling motion is where you have an object that has a circular kind of cross-section that moves across a surface. That surface necessarily must have some friction on it in order for the object to roll without sliding. If instead we had a surface with no friction and this object were launched with a certain horizontal velocity across the surface, then it would just slide and there would be no rotation at all, because there wouldn't be any frictional force to cause it to rotate. So pure rolling motion, which is the one that we're going to consider, occurs when there isn't any slipping or skidding of the object across the surface. The reason for that is the static friction grabs the object so that it rotates as it rolls across the surface in a way that there's no sliding at the point of contact. Due to static friction, when we have pure rolling motion and there's no slipping, then that point of contact with the surface is a fixed point. The point on the rim is moving through space as the object rotates, but when it reaches the point of contact, instantaneously, for just a second, it stops before continuing to move again. And so the motion of a point on the circumference of a rolling object is kind of a complicated looping motion like this, but when the point of contact, when the point on the surface of the cylinder or the sphere reaches the point of contact with the surface, that's where it stops for just an instant. So that's pure rolling motion, and we can derive a very important relationship for pure rolling motion by considering the motion of the center of mass of the object relative to this fixed point. So omega is the rotational velocity of that object, and if we realize that the velocity of a point on the object is equal to its distance from the axis multiplied by omega, if we think of the axis being at the point of contact, which is the fixed point, then v center of mass is equal to that distance r times omega. And so for the center of mass, we find that the velocity of the center of mass is equal to the radius of the object, cylinder or sphere, times omega. And that's an important relationship that defines what it means to have motion without slipping, or pure rolling motion. Now, we can also, for this kind of an object, think of its motion as being combined, as being a combination of a rotational motion about the center of mass with a rotational velocity omega, and then a translational motion of the center of mass as it rolls across the surface. And it's very intuitive to write down the total kinetic energy as a translational component and then a rotational part. And so the translational kinetic energy would be 1/2 the mass times the velocity of the center of mass squared, and then the rotational part, we already know that expression, is 1/2 I times the rotational velocity squared. And this equation makes a lot of intuitive sense. It's actually proved more rigorously in your textbook, and so you can take a look at that if you want to see for sure exactly how this comes about. But it's a very useful equation that we can use, and we can only use it in this case of pure rolling motion with no slipping. What you'll see is that we can use the kinetic energy expression, and then we can also substitute into that the velocity of the center of mass right into the VCM squared term. And when we do that, we'll end up with the sum of two terms that both depend on omega. And omega is often one of the quantities that we're either trying to solve for or that we're given some information about in these kinds of problems. So here's the example that I'm going to do in class. A sphere of mass m and radius r initially rolls with center of mass speed v0 on a level surface. How far up a curved surface will the center of mass roll if it does not slip or does not slide? So here we have this sphere. Think of it as a marble. I believe you might have a homework problem like this as well. It's projected along the horizontal part of the surface with a center of mass velocity v0, and of course as it begins to rise up the curved surface, it loses some of its kinetic energy. It's going to slow down, and eventually it will stop. And this is a classic case of kinetic energy being lost as potential energy is gained. So it's a problem that's tailor-made for using the conservation of energy, and we'll just do that. And the one new factor that we'll take into account is the rotational kinetic energy that this object has, in addition to the translational kinetic energy of the center of mass. I hope this has been helpful. I know it's a lot of new information. You might want to listen to parts of this again, but I hope it helps you understand how we can treat rigorously rolling motion. And I'll see you in class.